Let's take a look at the idea of functions that agree at all but one point. So let's go through this theorem and then try to dissect it and understand what it's really saying. Let C be a real number and let f of x equal g of x for all x not equal to c in an open interval that contains c. So in other words, in some open interval containing c, f of x equals g of x everywhere except at c. When x equals c, then these guys actually have some type of different value. Now, if the limit as x approaches c of g of x exists, then the limit as x approaches c of f of x also exists, and here comes the important part, the limit as x approaches c of g of x is equal to the limit as x approaches c of f of x. Now, this may seem like a mouthful. It's like, what on earth are we talking about? This is actually incredibly powerful. And let me get rid of that. So let's jump into a quick example here and see why this is such a powerful theorem. Let's take a look at the limit as x approaches 1 of x cubed minus 1 over x minus 1. Well, we know this is a rational function, so really all I have to do is evaluate this at x equals 1. When I do, I'll get 1 cubed minus 1 divided by 1 minus 1, which is 0 over 0. Now, just as a reminder, this is not equal to 1. That would be a huge, huge, huge no-no. Okay, 0 over 0 is an indeterminate form, and we'll talk a great deal more about indeterminate forms. But right now, what you need to know is when you have a 0 in the denominator, you know there's an issue. And the 0 in the numerator does not make it equal to 1. Any number divided by itself is equal to 1 except 0. So, this is an exception to being able to simply substitute in this value of c, which is 1, into the rational function and get the limit. I have to do something different. And that's where this theorem comes into play. Well, first thing I want to do is I'm going to factor this out. So I'm going to have, see, x cubed minus 1, that factors to, I better put this limit back, the limit as x approaches 1 of, see, this could be x minus 1 times x squared plus x plus 1. That's the factorization of the difference of cubes here, because this is x cubed minus 1 is the same as x cubed minus 1 cubed, because 1 cubed is 1. So this is really the difference of cubes. So there's a factorization for it, and then I have the denominator still x minus 1. And see, this x minus 1 is what's causing the problem, because when x approaches 1, I get 0 in the denominator. I'm approaching 0, so that's the issue. However, when I factor it out like this, I can see that these cancel. And what I end up with is this is equal to the limit as x approaches 1 of what's left, x squared plus x plus 1. Now, what I want you to note is that I want to think of this as this right here being f of x. This right here is g of x. See, these two guys are equal for all x provided x is not equal to 1. Because if I make x equal to 1, f of x is 0 over 0. We don't even know what that means. But if I make x equal to 1 here, I get 1 plus 1 plus 1. Well, that's 3. So if I finish up this limit, I actually get this limit as being equal to 3. So what this is saying is, I'm going to rewrite this again real quickly here. This is equal to the limit as x approaches 1 of g of x, which is 3. Now, f of x is equal to g of x everywhere except at this one point where x equals negative 1. So what that means is the limit as x approaches 1 of g of x is equal to the limit as x approaches 1 of f of x. Even though I can't find f of x directly, I can find it through the limit of g of x as x approaches 1. G of x and f of x are sometimes referred to as equivalent functions. They are equal everywhere. If you create a graph of f of x and then overlay g of x, you won't notice the difference. You won't see what's going on there. You won't tell. You won't be able to tell that there's two different functions there. Because what really happens is when x equals 1, there's a hole in this function. This thing's going to look like a quadratic, some type of parabola. And when x equals 1, I don't know where it really is. I haven't actually drawn this out or graphed it, but let's just say x is 1 right here. There's simply a hole there. So you really can't see the difference. But that's exactly why the limit is the same for f of x and g of x. So let's go ahead and take a look at another example here. I want the limit as x approaches 9 of x minus 9 over the square root of x minus 3. Well, this is going to be equal to, I just go ahead and evaluate this at 9. I have 9 minus 9. That's 0. Who cares? 0 in the numerator is fine. It's just going to give me 0. This is the square root of 9 minus 3. Well, this is 0 over, or square root of 9 is 3. So this is 3 minus 3. So this is 0 over 0. So again, I have an issue. So what I need to do is figure out another way to go about finding this limit. So I need to do a little bit of algebra. So what I'm going to do is I'm going to take x minus 9 divided by the square root of x minus 3. And I'm going to recognize that I can actually look at x minus 9 as being the difference of squares. If I write this as the square root of x squared, because the square root of x squared is x, correct? Minus 9, but 9 is 3 squared. And then this is divided by the square root of x minus 3. So this is the difference of squares. So in the numerator, I will have the square root of x minus 3 times the square root of x plus 3, all divided by the square root of x minus 3. And just like in the previous example, it was nice, that cancels out. So what do I get? I get the square root of x plus 3. So what this is telling me from that theorem is that the limit as x approaches 9 of x minus 9 divided by the square root of x minus 3. Oh, and I should also add to this, these are equivalent for x not equal to 9. Because when x equals 9, this function's different. I get that 0 over 0 thing going on there. So the limit as x approaches 9 of x minus 9 divided by the square root of x minus 3 is equal to, I'm thinking of this as f of x, the limit as x approaches 9 of the square root of x plus 3. And I'm thinking of this as g of x. Now, f of x is equal to g of x everywhere except when x is equal to 9. When x equals 9, I have this 0 over 0 situation. But when x equals 9 here, I get the square root of 9, which is 3, plus 3. So this limit is 6. So the limit as x approaches 9 of g of x is 6, which is also going to be the limit as x approaches 9 of f of x. So my original limit is, in fact, 6. Okay, let's take a look at this next one. Find the limit as x approaches 1 over x cubed plus 1 over x minus 1. It's very similar to the very first one that we did. In this case, I have x cubed plus 1 and I have x minus 1. So if I simply let x go to 1, what I end up with is 1 cubed plus 1 divided by 1 minus 1. Well, that's 2 over 0. Well, clearly 2 over 0 is a problem, but it's not the same problem as 0 over 0. 0 over 0 is an indeterminate form. So what I really need to do is take a look at this a little bit closer and break this down in terms of f and g. So I want the limit as x approaches 1 of f of x over g of x, where obviously f of x is going to be x cubed plus 1 and g of x is going to be x minus 1. So this is true for g of 1 non-zero. Or in general terms, I'm going to change this to a c, g of c non-zero. That's really what I should be talking about here. Okay, so let's try some stuff like we did earlier. Let's consider the limit as x approaches 1. This is a sum of cubes. The sum of cubes will factor out. So this is x plus 1 times x squared minus x plus 1 over x minus 1. Nothing factors out here. I can't cancel anything, so this did not help. But, I mean, it's a logical approach to take. So, let's start looking at basic idea of limits. So, I want to take a look at the limit as x approaches 1 from the left of x cubed plus 1 over x minus 1. Now, the numerator will go to 2. As I approach 1 from the left, I'll get 1 plus 1, which is 2. The denominator, like we already said, approaches 0. But when I approach 1 from the left, I have a value, this x value will always be less than 1. So I'm going to end up with something less than 1 minus 1. I'm going to end up with something that always less than 0. In other words, it's negative. So although I approach 0, the denominator is always going to be negative when I approach from the left. So what that's telling me is in that this limit ends up being negative infinity. Because what's happening is I'm getting 2 in the numerator and something incredibly small in the denominator, which means this thing's getting huge. But the denominator is negative, so it's getting huge negative. It's going to negative infinity. Well, right away, if it's going to negative infinity, we know that limits have to be a real number. So this limit from the left does not exist. It's negative infinity. All right, so what happens from the right? I need to take a look at the limit as x approaches 1 from the right of x cubed plus 1 over x minus 1. Again, the numerator will go to 2. The denominator will go to 0, but greater than 0. In other words, it's going to be positive. As I approach 1 from the right, this x value is always going to be bigger than 1. When I subtract 1 from it, I'm going to have something positive. So what I'm going to end up with is something positive in the numerator, something positive in the denominator, but the denominator is getting incredibly small, which means this ratio is getting incredibly huge. Therefore, this is telling me that my limit is actually going to positive infinity, which, again, doesn't exist. So the limit as x approaches 1 of x cubed plus 1 over x minus 1 does not exist. When I approach from the left, I go to negative infinity. So if I had to graph it, when I approach x equals 1, I don't know what it's doing here, but I know as I approach 1 from the left, this thing is shooting down. It's going to negative infinity. And as I approach, I should label that as 1 from the right, I know this is shooting to positive infinity. Well, what I'm getting is a vertical asymptote at x equals 1.